I am Hao Zhong from Shanghai Jiaotong University. The title of my paper is Enriching Compiler Testing with Real Program from Bug Report. In this paper, we report our experience to test compilers with real program from bug reports. First of all, let me introduce the background. Programmers write source files in programming languages, for example, C++. The syntaxes of programming languages are close to those of natural languages. However, machines cannot directly understand source files. As an intermediate between programmers and machines, compilers are widely used to translate source files to binary files. The translation is important, but as software artifacts, compilers can have bugs. For example, they can crash. They can also reject valid programs and generate wrong code. The bugs in compilers can cause bugs in the compiled code. It is quite challenging to detect such bugs. To resolve the problem, researchers have published many papers on compiler testing. According to a recent survey, more than a half of papers work on the generation of test programs. The existing tools generate two types of test programs. One type is random code. For example, C. Smith can randomly generate C and C++ code. The other is muted code. For example, after it records the executed length of a program, EMI changes untouched code length to generate more test program. They compare the outputs of original programs and mutated programs to find bugs. Random code and mutated code are both unreal code. Generating unreal code is actually a limitation of these tools. For example, all these tools remove invalid programs. Although invalid programs can be useful, programmers can never write such invalid programs. To avoid criticism, researchers choose to ignore them. That's the background of our study. Now, let me introduce our research methodology. My paper is not an approach paper. It is not an empirical study either. It is an experience report. According to the call for papers, experience papers describe a significant experience in applying automated software engineering technology. According to the listed criteria of the call for papers, I introduce my work from 4 angles, such as the problem, the insight, the tool, and the lesson. I next introduce a problem. The problem is that researchers either generate random programs or mutated programs. However, if test programs are real, it is easier to understand the importance and the relevance of compiler bugs. Although they are beneficial, most real programs are ineffective to detect compiler bugs. Indeed, I found that a paper has used both random and real programs. In this PLDI paper, researchers use both types of programs as the seeds of their mutation. In their evaluation results, from mutated real programs, they detect only one bug. If we want to use real programs to test compilers, we must find a better source to extract real programs. Now I introduce our insight. We notice that it is feasible to extract many effective real programs from compiler bug reports. First, bug reports contain many real programs. From such programs, programmers can analyze the importance and the relevance of compiler bugs. Second, these programs are effective. They are reported since they are believed to trigger compiler bugs. Third, most programs are submitted to only one compiler. These programs can detect more bugs in other compilers. Finally, many bug reports are fixed. Their compilation results can be used as a golden standard to test other compilers. Considering all these points, in this study, we analyze how to test compilers with programs from bug reports. Our tool is built on two software engineering techniques such as the extraction of code snippets and differential testing. Given a bug report, it classifies its paragraphs into three categories such as programs, descriptions, and others. After programs are extracted, it uses differential testing to detect bugs. From each paragraph, our tool extracts three types of features, such as structure features, word features, and punctuation features. This table on the right lists our features. Our underlying classifier is classical. It is a combination of decision tree and ADA boost. Please refer to our paper if you need to know more details. To evaluate the effectiveness of our tool, we build a benchmark and conduct a tenfold cross-validation. The results are positive. However, we are more ambitious. Our work is not limited to the results on benchmarks. We next introduce our experience report. In our experience report, we select the two state-of-the-practice compilers such as GCC and Clam. We build the two compilers directly from their latest source files. Their versions are not that new, only because the publication process of this paper is too long. As for bug reports, in total, we download more than 9,000 GCC bug reports and more than 3,000 Clam bug reports. Can we detect new bugs if we follow our research idea? My answer is yes. First of all, it is not strange that we found some similar bugs. In this example, the program from a Clam bug report triggers a quite similar bug on GCC. Indeed, when we report this GCC bug, we even copy some sentences from the original Clam bug report. Still, we found more different bugs. In this example, the program was extracted from a Clam bug report. It is invalid. Clam crashes when it compiles this program. We extract this program and use it to test the GCC. GCC does not crash, but it believes that this program is legal. It compiles it without any warnings. As GCC crashes, as Clam crashes, but GCC accepts this program triggers a different GCC bug. Some of our found bugs are marked as duplicated. However, we found that some duplicate bugs are also useful. In this example, we report a bug report to GCC, but our bug report is marked as duplicate with an old GCC bug. This old GCC bug was reported 5 years ago. It has not been fixed until our bug is reported. Indeed, only after 1 week after we report our bug, this old GCC bug is finally fixed. We found some non-standing bugs. For example, this program first appeared in a GCC bug report in 2007. It reappeared in a CLAN bug report in 2010. Both bug reports are marked as fixed. However, we found that this program still triggers bugs in the latest compilers. A GCC programmer confirms that this is an undefined behavior. It can be fully fixed only after the behavior is defined. We also found some controversial programs. In this example, the program is accepted by GCC 4.8, 5.2, and 9.0. It is also accepted by CLAN 3.6. However, the same program is rejected by GCC 6.0 and CLAN 7.0. After we report this bug, it is marked as duplicate. However, it is not fixed. Is this program legal or not? We still have no answers. Even the latest GCC and CLAN disagree with the result. In total, we found 156 bugs. Among them, 103 are confirmed. Most of our found bugs are accept invalid bugs. That is, our reported programs are invalid, but these compilers compile them without any warnings. As we introduced before, existing tools removed all invalid programs. As a result, they cannot find this type of bugs. However, our study shows that in real development, programmers can write such invalid bugs. As a result, invalid programs are useful. In summary, our results show that our research idea is quite effective. We also learned some lessons on differential testing. Some of our bug reports are marked as invalid. In C++, some behaviors are undefined. Some defined behaviors are controversial. Also, our bug reports are marked as invalid. These invalid bug reports can reveal some deeper problems in C++ and its specifications. We list such bugs in our paper. Let me summarize my work. Researchers often use random code or mutated code to test compilers, but it is more beneficial to use real programs. However, most real programs are ineffective to detect bugs. In this study, we identify that bug reports can contain many useful programs for compiler testing. Following our idea, we found more than 100 bugs in the latest versions of GCC and CLAN. We also identified the limitation of differential testing, since some behaviors are undefined or controversial. That's all for my presentation. If you have any questions, please contact me through my email. Thank you.